very much, Chairman. Good evening. Welcome to this discussion forum also from my side. So this evening we are expected to discuss advances in quantum technologies and what we expect from these advances. And I would like to pick out one particular example where advances in quantum technologies could make really a difference. And this is actually the bottom-up design of unconventional superconductors in magnet superconductor hybrid systems. So this is actually based on earlier work in our group going back 15 years in time on atomic scale spin structures built up atom by atom with the help of a scanning tunneling microscope tip. So we started actually some time ago to build up nanostructures like chains, but also 2D assemblies, for instance, of magnetic atoms like here, iron atoms on a platinum single crystal substrate. And what we can do is we can really predefine the distances between the atoms. We can, of course, also select the species here. We can select the substrates. In this case, we have purposely chosen a substrate where we expect high spin orbit coupling. And that has an influence actually on the spin texture of this chain, because as we will see, we will not have a typical collinear state as we would expect for iron, but we have a non-collinear state. So the beauty is that we can not only do atom manipulation with the help of a scanning tunneling microscope tip, but we can also perform spin-resolved imaging on the atomic level. So this is the spin-polarized map of that chain of iron atoms, and you see here that there is here a drastic change in intensity of measured spin-related signal. It's in fact the spin-resolved tunneling conductance which we measure between the STM tip and this nanostructure. And you see that here the intensity is low, then it gets very bright, then low, then bright. But then you see it's not fully periodic. And if we look at a line section across this chain here, which is plotted here, you see that this is typically a beating pattern resulting from the superposition of two spatial frequencies. Namely, a short period wavelength, which is coming from the interferomagnetic short-range coupling. And this is primarily determined by the RKKY interaction between the iron atoms on the platinum substrate mediated by the platinum, and a superimposed long wavelength period, obviously, and this is actually due to the interfacial Dzerzhinsky-Maria interaction for that system. Now, the beauty is that we have been mapping out the distance dependence of the RKKY interaction as well as the Dzerzhinsky-Maria interaction, independence of the crystallographic directions and as a function of spacings. And so what we could do in the past years is really design such kind of spin spiral states, not only for one-dimensional systems, but we also discovered, for instance, two-dimensional skyrmions in ultra-thin films like iron monolayers on iridium and many others, due to the insight into the atomic scale fundamental interactions like RKKY and Dzerzhinsky-Maria. So that was very important, of course, and that was actually already here the topic of a plenary, by the way, at the very nice ICSM conference at that time in 2012. Here you can see the organizer, Alec Genser, also attending that meeting. And how did that help in the following? Now, as you all know, there have been beautiful expectations and predictions by theory, actually making use of magnet superconductor hybrid systems to induce novel, exciting superconducting states. For instance, topological superconducting states in systems where you have a spiral state, just as you have seen it, but now interacting with an S-wave superconductor. So, of course, we have to replace platinum by something else, like niobium. It was a wonderful prediction, theoretically, because not only the topological superconducting phase was predicted, but also the so-called Majorana states, as I have reported on Monday. And so, by atom manipulation, we could build up these structures here, in this case, manganese chains on a niobium substrate in the superconducting state. and we could really map out the predicted zero energy modes here, very well separated from all the finite energy states, which are trivial. And we could even determine the topological nature of the gap structure. And this is seen here. As I explained on Monday, we do this by Bogoliubov quasi-particle interference and Fourier transformation afterwards. And so we could really map out for the very first time the in-gap band topology inside the gap of a superconductor, really showing extremely nice agreement between the experiment and the theoretical expectation for topological superconducting state for a quasi-one-dimensional system, and we could even determine the topological gap size. So this is what I reported in detail on Monday, as you know, but there have been many other nice predictions, and I would quickly like to go through. I have limited time. So in 2016, 6 years ago, the Princeton group of Bernevik made a very nice prediction about a topological superconducting state when you bring ferromagnetic islands in contact with an S-wave superconductor, and you expect then chiral Majorana edge modes along the periphery of these islands. Again, you can do a bottom-up approach and basically realize such a model type system, for instance, by iron monolayer islands on a superconducting rhenium substrate. What you expect is that within the superconducting gap, you have a chiral Majorana edge mode. So if you would look at the edges, you would, of course, expect to see intensity then, of course, which you would not be able to see in the bulk of the island. And this is exactly what you see beautifully here when you map this spectroscopically with the help of a tunneling microscope. Right at Fermi energy, you see this great intensity coming from this Majorana edge mode. You see induced gap here, a full pronounced gap. So the iron island becomes superconducting due to proximity with the rhenium substrate. And you see, of course, how the system develops if you go higher in energy towards the coherence peaks of the superconducting rhenium. And there was in beautiful agreement the theory by Dirk Moore and co-workers from Chicago. You can go on and look, for instance, for topological nodal point superconductivity, as has also been theoretically predicted. In this case, you can just go for manganese islands which have an antiferromagnetic ground state and interacting with a superconducting niobium substrate in this case. And the nodal point superconducting state, which was predicted, is beautifully reflected in the scanning tunneling spectroscopy maps, and you can prove that actually by looking at the different signatures of different edges. For an antiferromagnetic island, namely, you have ferromagnetic and antiferromagnetic edges, and also this kind of more open ferromagnetic edges. And the different edges show up differently here with different brightness, and you can read this in more detail in this publication. Finally, and this is another beautiful prediction by theory, in this case by Nagaosa and co-workers from Japan. They have predicted that if you bring a spin spiral state in contact, in proximity to an S-wave superconductor, you can also create a novel type of unconventional superconducting state, in this case a P-wave superconductor. And again, this system has been realized now also experimentally by one of my PhD students here. In this case, iron monolayer actually was grown on a superconducting tantalum substrate. Again, of course, it's clear why you have to go from niobium to tantalum, because tantalum offers higher spin-orbit coupling, so you increase the interfacial DMI, and this leads then to non-collinear ground states, not collinear ferromagnetic states, as you would expect for iron, but really these spin spiral states. So here in the spin polarized STM image, you can beautifully see these spirals with a period of 6 nanometers interacting with the superconducting tantalum substrate. So again, a very nice further example of a bottom-up approach. Now this is my final slide. What are the future perspectives? So we are really looking forward now to bottom-up design of something like a high TC superconductor, maybe not yet at the beginning at room temperature, but in a quasi two-dimensional magnet superconductor hybrid systems. So the idea is not to start with very complex materials where the physics might be very complex to describe, but really to have something like a minimal experimental model system and a minimal theoretical model to catch the basic physics of, say, such kind of high TC superconductor. So one example of promising model systems would be, for instance, a two-dimensional magnetic layer with antiferromagnetic spin fluctuations, which we can observe experimentally, proximatized on top of a BCS superconducting substrate. This is one of the model systems we are working on. So as I said, there are needs now for minimal theoretical models describing possible enhancements of BCS superconductivity by non-electron phonon mechanisms. The beauty is, as I showed you, these days, for any model type Hamiltonian, we can experimentally realize this from the bottom up, from individual atoms. So the accuracy now for condensed matter systems is exactly the same as for quantum optics. You all know that quantum optical systems, of course, have been used for quantum simulation already for quite some time now. But of course, quantum optical systems are different from condensed matter systems. But now we have the same kind of precision. We can really realize any kind of model Hamiltonian, as you have seen by the Kitaev model Hamiltonian, which we can realize now experimentally. So there are really great perspectives, I would say, for theory-guided quantum materials design due to all these advances in quantum technologies and especially in atomic scale technologies, which is what I wanted to say. Thank you very much.
The advances in nanoscale technology today open really a completely new windows for different world where we can control a nanoscale structure. This was an idea of, I think today was reminded by Teller. Teller wrote a paper in '87, said IBCO that should have a nanostructure, very particular one. And this is the trick for ITC superconductivity, but nobody was, but the majority, not nobody, I was very interested, but the majority of scientists took another direction. So now we continue this very interesting symposium with Jacopo Santamaria. Can you speak and you present? Okay.
Can I use a microphone?
Yeah, okay. Yeah, it's more simple because we try also to, you can interact and make the discussion. It's an open symposium.
Okay.
So, and also try to connect with the other speakers.
Actually, I think I will use.
Okay.
Can you hear me?
Yeah. We can hear.
It's not open. Okay.
Yeah.
Okay.
Yes.
Okay. So, good afternoon, everyone. When I was informed that I have to, it's not working. Okay. So then I take this one. Yeah. Very well. Now, so when I was informed that I had to participate in this panel discussion, I was thinking in the ways to connect my discussion here, my presentation, with my talk, which was on Josephson junctions, right? Which is, it would be an obvious thing to do when one tries to speak about quantum technologies, right? Josephson junction is a quantum device, so it should be easy to find a connection, right? But I mean, after the talk this morning of Professor Francesco Tafuri, we have learned already that there are a wide variety of novel kinds of Josephson junctions that may be so very interesting effects that could be used for quantum sensing and for many applications to build quantum beats, etc. So probably I wouldn't be able to add anything useful, right? So I decided to change gear in a sense and share with you a few thoughts, probably very, very naive, very primitive, right? And in which I would be happy if you interrupt me and you correct me and you add further on what I will try to share with you. So the idea is that, I mean, we enter the era of the quantum technologies, and there's many people that started already working in killing applications, in killing devices. They're trying to buy computers. I'm a materials guy, right? So somehow I have the feeling that we need quantum materials to build quantum technologies, right? And I was trying to prepare this talk. I was reading a recent article by Bob Cava in Chemical Reviews, where he was proposing that there is a sort of circular argument that one needs actually the quantum technologies to understand the quantum materials. I mean, if I would ask to this audience what is a quantum materials, they would be probably many different answers, right? But they would be in common that all of us can recognize a quantum material, the quantum Hall effect, the graphene, a topological insulator, macroscopically entangled system, quantum spin liquids, correlated materials, etc., right? The problem is that very few of the systems are understood in depth, right? The physics is not completely understood due to their complexity. And we are facing a moment in which we propose that quantum technologies will help us to understand the properties of quantum materials. And this is the circular argument, right? And the question is, do we need a revolution in quantum materials before we can face a revolution in quantum technologies? And this I would like you I would like to have your opinion on this. I mean, quantum materials, a minimum requirement is that they are quantum at macroscopic scale. So they, a part of their intrinsic complexity, they will interact very strongly with the environment, right? Eventually entangling with it, right? And what is the effect of disorder in quantum materials? So there is a number, of I think, very important questions that we should able to answer, right, before we can use these quantum materials for specific applications. And that's the reason probably because why people, I cannot connect specific quantum materials to applications other than the trivial devices, say, right? So this is basically what I wanted to say, and of course I would very much appreciate if you can add to this. If I manage to motivate you somehow, if you can add some arguments to that. I thank you very much for your attention.
Thank you, Jacopo. I would like to thank you for posing questions. So in your talk, you just don't declare sentence, but you open questions. So one question is, what is a quantum material? Quantum technology, we know, they go to very nanoscale size, like you presented in the previous talk. So I think we will continue the discussion. Thank you for opening the new questions.
Thank you.
Now, Thomas Hopper.
Yes, I also like to give.
You take the microphone and you come here. Take the microphone.
Okay, sure.
Take the microphone from Jacopo and come here.
Okay, let me take the microphone. I also like to contribute to this session about quantum technologies, and I may have a very different viewpoint to this in comparison to a lot of the participants of the conference, because they are coming from fundamental science, from research. This is also my background, but since about 10 years I'm managing a company. I have about 120 people, and our mission is to transfer results from scientific projects into industrial applications. So our customers are very innovative companies which are looking for new solutions. And in this case, I'm first of all responsible, of course, for the 120 people and for the success of the company. So most of our, let's say, successful business is based on classical but very advanced products based on semiconductor technology. But nevertheless, we are looking for the next generation of solutions. So we have three current activities which are based on quantum technologies. And we're also looking for those who have the potential to go to applications soon, because this is something which will be also very encouraging for young researchers, but also encouraging maybe for funding agencies to see that their money is going into some real products. So that's why I'm not addressing maybe some very advanced nanomaterials or things like this, but I will tell you the three different fields we are working on. So one is the quantum-based gravimeter. It's a sensor to detect holes or modes under the ground, and it's working in a quantum regime because the ratio of mass and spring constant is already in a quantum regime. And this was proposed about 10 years ago by a British group, and they showed maybe 2 by 2 meter table solution to build this on an optical table. And nobody was thinking this can be turned into a practical sensor. So our solution now is 2 by 2 centimeter, and we have the first 150 orders for this system from the German government to investigate the soil for new developed areas. And the second application field is based on diamond NV centers. I think this is a very popular field at the moment, but the question is what you build with it. We're also building a magnetic field sensor, but I don't want to point out it's very sensitive or very, let's say, high precision. This is all possible. People wrote papers about this, but so our sensor has one unique feature, and this is this behavior of the magnetic field versus the fluorescence modulation, and you have one feature which always occurs at the same field. So that's the reason why you can use it as a calibration-free sensor in applications. And the most attractive application which we have is at the moment smart meters. So there are companies, especially energy is an important issue, electrical energy at the moment, and they are afraid of people manipulating their meters, and they want to use different systems, not the classical magnetic system. They say this diamond-based magnetic field sensor has two features. First, it has this calibration-free operation, And second, it is physically much, much more complicated than the other system. It's based on some light, some optical detector, and so on. It's not so easy to manipulate. So we also have the first 1,500 orders for this sensor. So it goes into real applications. And the third one is based on solid-state circuits, so superconducting electronics is something I also gave a presentation on it. And it's a little bit harder to say how many, let's say, devices have been ordered by someone, but our business case is not selling the solid-state circuits based on Josephson junctions. In this case, our business case is system integration. So we offer flip chip assembly, smart attachment of optical fibers to the system. So it's very, let's say, classical, but very dedicated assembly and packaging for quantum systems. And I like to end this contribution with maybe two goals or two motivations I like to address, maybe on one side to leaders of groups and also to PhD students. I think the future of the world is not steered by politicians. We need engineers and scientists, so we need to motivate young people to go into engineering and science. Quantum technology is a very attractive field to motivate them. And then, when we have more and more, at the moment there's a strong demand. We need people, I would immediately hire people if I had, but we need to motivate the young people to go into this field. And I remember 20 years ago, they said, oh, no nuclear power. So a lot of physics students say, okay, what should I do now? So this motivation is important, but also we need to find applications for quantum technology which are maybe addressable in 2 or 3 years by first applications. Because otherwise we risk that we have, after this huge increase of funding right now, we have a valley after that, and we cannot show some success. So thank you.
Thank you very much for, I think, the mission to grow new generation in quantum technology and quantum science, I think, is our mission. So, and thank you very much for your work you are doing. Now we have another contribution from Joanna Skiba from United Kingdom. You can come.
Okay, I will start talking. Yeah. Brilliant. And thank you. So I'm a physicist, and I'm a physicist who works for a company. So I look at quantum technologies from the perspective of applications as well. So we share the same kind of base view. And my speciality is quantum emitters. So what I want to achieve in my work is to build a device that will have its application in quantum network systems. So I work with photons. I don't work with electrons. I work with photons that have spins. And I manipulate spins. Of those photons, basically I want to achieve my quantum based on entanglement of the photons. But first of all, I have to actually produce those photons. And I have to produce those photons on demand. And in order to do this, the very basic element for me is the material. And I wouldn't achieve it with simple structures, simple, not so simple, with structures like quantum dots. And I've prepared only one slide, but hopefully that will take me quite a long time to talk. So I wanted to tell you from my perspective, when I looked back at the topic recently, I found out actually how much has changed since the beginning of quantum dots. So Stransky-Krastanov quantum dots, they were first experimentally achieved more or less when I was born. I'm slightly older than them, so about 35 years ago. And first of all, actually, people started showing those spectra of ensembles of quantum dots. And then eventually, after whatever 20 years, eventually we ended up showing individual lines and started working with those individual lines. Also within those 20, 30 years, we found out that we can achieve those quantum dots, those single quantum dots, at different wavelengths, starting from, let's say, 600 nanometers up to even 2 microns, which was quite attractive. Obviously, this all depends on the material that we're using, on different configurations. But there were always challenges. We wanted to control the density of those quantum dots in order to address those single individual quantum dots. But we knew at the same time, once we managed to do this with one particular system of quantum dots, that they present to be very amazing single photon and entangled photon sources. Obviously, there were still like little kind of issues like fine structure splitting that is related to the dot elongation, coherence times of the photons. And also there was a big question, can we and when can we start mass manufacturing those quantum dots and putting them into proper devices? Oops. Then also, probably about 10, 20 years ago, once the single quantum dots were achieved, people started working towards site-controlled quantum dots. And there was a great talk today by Ian Farrer showing the latest achievements within this field, where University of Sheffield could achieve the control over the density of quantum dots by placing them in determined, predefined positions on the wafers. Obviously, this is a great advancement because once you know where the dot is, you can build amazing device around it. And obviously, the mass production problem is essentially, it's seeing a light at the end of the tunnel, because potentially the site-controlled quantum dots, they can definitely help. That could be useful. Obviously, there are still questions whether these site-controlled quantum dots, whether they will have improved fine structure splitting, what will be their line width, what will be their optical properties in general. But this is all something that will most certainly will be resolved over time. Then the next step forward, I believe a massive breakthrough, was inventing the new technology of growing such quantum dots. This is a new kind of type of quantum dots called droplet quantum dots. So in principle, they look the same, except of the fact that this is SEM image, this is AFM image. They are also randomly nucleated, but the growth mechanism is completely different. I'm not going to tell you right now the details, but the great progress and advance of the droplet quantum dots is the fact that we've shown that they have amazing extended coherence times, very much improved fine structure splitting. They can reach telecom wavelengths easily, which means they are compatible with existing fiber optics infrastructure available like literally everywhere. And then finally, in the talk presented today by John Heffernan, we found out that there's been some first attempts of trying to combine the two, the droplets and site control quantum dots. And essentially, they've managed to show that they respond to basically finding the lowest potential energy on the surface of the wafers. The droplet like to kind of form themselves within the pit. Everything, this is kind of, they present about 70% occupancy within a certain area. And I believe that, you know, if we tick all those boxes, that could be the holy grail of quantum technology in terms of photons and manipulations of the photons. So, yeah, from my perspective and from the perspective of a person who plays with photons, I believe this is something worth stressing, that, yeah, we've got materials, we've got technology. If we combine the two, we end up with amazing features that can be later on, well, incorporated into devices and used to have proper applications in quantum technologies. Thank you.
Thank you, Joanna. I think it is really quantum physics. I've been pleased this morning to follow your session. It was very beautiful, yeah, very, very, very stimulating. And I would like to connect your talk with your previous speakers. I think that we have to increase much more the interaction between fundamental physics and application, because the example that always I do is that if I calculate the airplane and I have only theoretical equations, I will never go up you will never go in a plane. Only when you see the plane is working, yeah, that you believe. So I think technology is fundamental for realization of the impact of science for the community. So because we scientists, we like to do science, but we have also to produce device for the community, and the joint contact of fundamental theory, fundamental physics, and application should be really work a lot. We should do even much more what we do. So thank you for your talk, Joanna.
Yes, exactly. It's I think, for me, it all kind of starts with application. If you have an idea, I mean, my approach to it, just try it. Mm-hmm. Try it. Yeah. If it works, if it has a chance, slightest chance to work, you can always actually improve it by adding some simulations and, you know, improving certain parameters. But, yeah, just get your hands dirty and...
yes, I agree completely with you.
Yeah, and get the feeling first of all.
I know.
Thanks.
So now we have next speaker. That is Valerie Vinokur. And now we go to quantum theory.
Okay, good evening, and well, thank you for, well, coming here despite this late hour. And okay, now I am working for, okay, let's see, it's this. Okay, for the company Terra Quantum, which is doing a variety of Terra Quantum technologies, and I'm Chief Technology Officer in the US. And the spectrum of what we're doing actually is quite wide. And I will try to, okay, to give you like impression of what we're doing. So we started as a startup, and we exist about, Misha, how many years? 3 years, okay. Well, we were usual startup with a capital of like 3 million. Now we raised to 90, and the amount of people working for our company increased accordingly. And what we're doing, well, One of our directions is quantum computing and security. And then we have, as we call it conditionally, 3 pillars. One is quantum algorithms. It's here. And we developed new hybrid quantum algorithms manifesting enhanced speed and combining most advanced quantum and classical methods of computations and capable of solving the problems which were considered to be most hard, like problems of optimization for finance and science. And we have like, okay, another our representative, Michael Perlstein here, who can tell you much more detail about this pillar. Then we have quantum computing. We are utilizing and we work together with QMware, and we have hybrid quantum cloud. And basically what we're doing, we develop hybrid structures. And we also develop our own quantum processing units with the unique, again, our development hybrid architectures. And then another pillar of this computation and security is quantum communications, new protocols and encryption libraries, which actually, and about this I'll tell maybe in a little bit more detail. We promise complete 100% secure storage and communication of the data over large distances, absolutely unavailable to anybody else. Okay, so this is like one of the examples. So we have optimization problems, and this shows how well we're, let's say, proceeding with this. We have machine learning. Actually, one of our directions is machine learning and artificial intelligence. And again, this is okay, shows advance of our technologies which we use. And we have, and one of the things we are doing, we are capable of solving linear algebra and nonlinear differential equations in the volume which was absolutely unavailable before. And again, this comparison shows how well we are doing. As I said, we interact with this QMware hybrid quantum cloud, and we also develop hardware. So one of these hardwares is ferroelectric-based field effect transistors. This was actually the main content of my talk, so I just mention it. And another thing which we're doing is we develop new superconducting qubits, which we believe will be able to work at elevated temperature. So quantum computers which we have now work at very low temperatures, so it's great, but it will be even better if we will be able to work, let's say, at 10 Kelvin instead of 10 millikelvin. And this is one of our directions. And okay, this is how we work with the client. Actually, we have clients, and we offer to them access to everything what we are doing. It's just the list of what we are doing and to what we offer them an access. And what the thing at which I would like to, let's say, stop with a little bit more detail, this is, okay, quantum encryption and this secure quantum communication. Well, if you just open any press release or any advertisement of these quantum companies, you'll find out immediate communication that our glamour future is quantum computing, when we'll have quantum computers at our disposal at every household kitchen. And this is absolutely great, but then there is a negative side of this glamour future, which means that these quantum computers will be able to break down any, let's say, encryption, any ciphering, and they're so powerful that there is no protection against them. And what we're saying, that we develop the 100% protection against these quantum okay, hypothetical quantum computer break in. And not enough, what we can do, we can provide the safe communication over global distances, which is again not available to anybody, I believe. Well, beautiful picture. Well, we cannot win 3 times around the globe, but we can do it 1 time. Well, it's just like, okay, artistic. This is artistic enhancement, but just okay, to be more convincing. And basically, it was okay. It was mentioned pretty well that it's good to have fundamental physics, a connection of fundamental physics and applications. And this is exactly like, okay, and this is exactly how our Terra Quantum started. One of the most fundamental problems, let's say, in life and in physics is the origin of irreversibility. Because we know that all the laws of physics and all the laws of nature are invariant with respect to change of the sign of the time. But if we can change the sign of the time and nothing happens to these fundamental laws, then the question immediately appears why we are aging, but nobody could see, okay, well, except for science fiction movies, of course, why we only age, but nobody saw us getting younger. Small contradiction. The key how to solve this problem was, the guess was done by 2 great people, Landau and von Neumann, independently about 100 years ago. And the solution, okay, comes from indeed quantum mechanics. And we, okay, wrote a paper which was like pure abstract paper explaining where irreversibility appears in our life. Since it was like beautiful theoretical paper, always, of course, it's a question whether we can, okay, test our beautiful theories in experiment, and it was done. And how can it be done? Since we knew the algorithm by which universe can only age, if we know this algorithm, then we have to be able to like turn it around and make things younger. And this actually was done. This was, okay, we found a system, controlled quantum system, which we could evolve back in time, and we did it. This, well, okay, this was covered in New York Times and other, let's say, media. And this was exactly 2 fundamental works from which we derived our new approach to cryptography. And it was completely change of the paradigm of cryptography and the protection, because all the existing methods are based, let's say, on the mathematical approach. I mean, okay, we don't have enough time, so I'll be just crude. Okay, so to invent the more and more sophisticated, okay, way of ciphering or encryption, well, then people invent how to break it, to break the code, then, okay, new thing is invented. And our approach was completely different. We took approach based on not on mathematical, okay, tricks, but on physics, and based on the fact that we can completely control the line of communications, this fiber optics, on a long distances. And since we can control it, we can immediately find the moment when we have the interference. Okay, sorry. Coming back. And this is like, okay, this is the scheme of how our safe communication does work. So, okay, you know this. We have Alice who is sending the message. We have Bob who is, okay, suppose who is the receiver. And we have eavesdroppers, who is Eve, just by this like accepted, okay, notation. And this is basically our line. So without going into much of the detail, we immediately, what we can do, we developed new kind of quantum key distributions and new protocols. And basically what we do, since when we send coherent quantum state along the line, we immediately know if someone is trying to interfere because, okay, this is the foundation of quantum mechanics. If we measure the state, then we change the quantum state. So if someone interferes, we immediately know about that. And then we can adapt our protocol, just decreasing the number of the photons in the coherent state which we send along the line. And then what happens if the intercepted signal, okay, is small, we can decrease it to the degree when it will be only a couple of photons, okay, intercepted by Eve. And if it's only a couple of photons, again, to be simple, then quantum fluctuations become enormous and they completely bury the information which was transmitted by these photons. So this is our approach. And this is just a quantization of our approach. If the intercepted signal is small, then we have a very high speed of transmitting the signal, 1 gigabit per second. If it will be 0.1% of intercepted, then the rate of the transmission is a little bit less, but still quite impressive. And we can go over these 40,000 kilometers being absolutely secure. So this is one of the examples, probably one of the most striking, and therefore this is what we're doing in all the directions. Thank you very much.
Thank you, Valerie, for such a fantastic perspectives. And we have seen another company growing up. I think it's very important for us.
Sorry?
Thank you for presenting your Terra Quantum project. I think it's very fantastic and very promising.
Thank you.
We're now open discussion, so between if there are questions, and we can start to have interaction also between you. So also you can ask questions to your colleagues in the panel. Or you have some questions?
My voice is not so good, sorry. I'm trying to work. And I have two questions to all, so maybe. What is the coherence time for the entanglement in your applications? I mean, what time scales we are talking about, and for each application in Terra Quantum, for example, what are the prototypes we have? And
Okay, we don't send entangled photons actually, because the distance is much too high. So we send coherent state, and so it works like that. We send it to 50 kilometers. Actually, I can't tell you much, but there are some big company in the United States for which we are installing this system. So we were successful to install it for, let's say, their local campus, so to say. And now we are establishing this network in the United States. And it works like that. We send the signal over about 50 kilometers distance, coherent state, and, well, I mean, it remains to be coherent over the whole distance. Then we have amplifier, which you saw in this scheme, and then the signal is amplified and the new coherent signal, sent off again. So basically, this coherence is infinite, but it's a coherent state, not an entanglement. We don't use this, entanglement phenomena for that.
Well, same to you,
Sorry?
Thomas. Same question to Thomas. I mean, well,
but the coherent state, it lives, infinitely long, so to say, because it goes for 50 kilometers, it is taken by amplifier, and then the new coherent state is sent, over the next segment.
okay. Thank you.
So I can also not give a, let's say, a straight answer for the gravitational sensor. It's an ensemble of quantum effects. So the measurement time is about a microsecond, but it requires averaging over time. And in case of the diamond NV centers, again, we don't use a single center. We use millions of center and measure the fluorescence sensor. It's not a qubit application. And in terms of the solid-state superconducting circuit, then it was also presented on the conference already what is the typical decoherence time in superconducting qubits. So that's very similar. But we also have this combination of the qubits, their entanglement with neighboring qubits, and the interference with the classical electronics, like the adiabatic quantum flux parametron electronics. And there was yesterday also the question about ringing time and how does this, let's say, control electronic interfere. And therefore we using, let's say, continuous operation between 1 and 10 nanoseconds.
Okay, so for our applications, we are limited by the detector's jitter. And we need our quantum dots to have coherence times at least 100 picoseconds. This is fairly, well, this is quite difficult to achieve with standard SK quantum dots. But with droplet epitaxy and droplet quantum dots, we were able to multiply that by a factor of 3, 4, 5. The longest coherence times that we see for our droplet epitaxy quantum dots is probably about nanoseconds, which is a total breakthrough and makes it extremely attractive for quantum applications.
There are some questions from the audience. Okay, so if there is no questions, we can close the session. Thank you very much. It was really, really important moment of the conference, this one, because we have seen how science and technology can go together. Thank you very much to all the speakers. Thank you very much.
I think we can repeat the last night. We can go to Terrace Bar again, okay? Where are we? Here. Or we can go to Terrace Bar again. We can go to drinking, Terrace Bar.